This video has sound. Hopefully everybody can hear it. Otherwise they're making arrangements to get it going. This is the 441, Chapter 4, Section 4, Part 1 lesson out of the Geometry Chapter 4 study guide. And at the beginning of the chapter we talked about how to establish that two triangles are congruent. First we said, well, if you can prove that you see 3 pairs of corresponding sides and 3 pairs of corresponding angles that are all congruent, you have all 6 things, that those two triangles have to be congruent. And then in section 4.3, I said, well, we do have these things called shortcut theorems, where you don't have to prove all 6 things congruent. You just need to prove some of them. And the first shortcut theorem says that if you can prove 3 pairs of corresponding sides, 1 pair, 2 pair, 3 pairs of corresponding sides congruent, then you don't actually have to focus on the angles. All you have to do is find 3 pairs of corresponding sides that are congruent, and then you can go ahead and jump right to the fact that those 2 triangles would have to be congruent. This is shortcut theorem number 2. It's called side angle side. And this postulate, we have to find 2 sides that have pairs of corresponding angles going from one triangle to the other, and then the angle in the middle between those 2. So notice, and this is really, really key, this is important, that the angle in side angle side has to be in between the 2 sides. So if we can establish that side RS is congruent to UV, and angle R is congruent to angle U, and side RT is congruent to angle side UW, then we can state, according to the side angle side congruence postulate, the triangle RST is congruent to triangle UVW. Okay. So in the diagram, ABCD is a rectangle. What can you conclude about triangle ABC? I'm assuming this is corner B right there. Oops, I'm sorry, corner D right there, not corner B. And triangle CDA. All right. Well, are they congruent? Are they not? Well, if it's a rectangle, then this side right here would have to be congruent to that one. So I could mark side DC congruent to side AB. And I also know that these 2 sides are parallel. Remember how we mark parallel sides? We use a little arrow symbol. And I know that this side is congruent with itself. And then if these 2 sides are parallel, and this side is a transversal cutting through, then I know that this angle right here, angle BAC, must be congruent to this angle down here, angle ACD, because these 2 are alternate interior angles. And all alternate interior angles that are placed next to transversal through 2 parallel lines are congruent. So I have a side here, AB, and an angle here, and then a side here. So I have a side on the top triangle here, an angle, and then a side that corresponds to other congruent sides and angles. So I have a side, and then I have on the bottom triangle an angle in the corner, then I have a side. So up here, the top triangle, I have a side angle side that matches up with a side angle side congruence down there. Notice that as I go around the triangle, side angle side, the angle is the second thing, side angle side. So by side angle side, triangle ABC is indeed congruent to triangle CDA. How about the rest of these, 7, 8, and 9? Can we use the side angle side congruence postulate? Well, I have AE, that's a side, that's always congruent with itself, so that's one pair of sides. I have this side congruent to this side, and then I have this angle congruent to this angle. So in the bottom triangle, I have these three things. And that would be either ASS, which is amusing, and SSA. Does that match that? Side angle side? If you read it either one way or the other, ASS or SSA, does that match? No. And that's really the same thing we have on the top here. We have either ASS or SSA, depending on which direction you read it, going around the outside of the triangle. So even if we could prove, you know, that we have AE congruent to AE, there's nothing else that would help us to actually get this pattern, side, angle in between, side. So can we use this theorem to prove these two triangles congruent? No. How about number 8? We have this side congruent to that side. So we have a side congruence pair here. We have this angle congruent to that angle, so we have a pair of congruent angles. And then we have this side congruent to this side. So we have, on this triangle, we have side, angle, side. And on this triangle, we have side, angle, side. Ah, yes. We can use side, angle, side to prove these two triangles are congruent. And then on this one, we simply don't have enough information. We could say that this is a 90-degree angle and this is a 90-degree angle, so we'd have a pair of angles that are congruent. And we could prove that JM is congruent to itself, so we'd have a side and a side. But that's it. That's all we've got. We only have kind of two pairs of correspondences here that are congruent. There's nothing else that we can state. So just based on the fact that we have a limited amount of information for number 9, we'd have to say no. We cannot use this theorem to prove them congruent. So here's a couple of, we're going to do 4 proofs using the side angle side congruence postulate. It's going to be important that you pay attention to the directions because they're really going to give you good hints as to how to do the proof. Some of them will say, hey, use the side angle side postulate. Or some of them will say, hey, use the you know, side congruence postulate, like they did over here. Use this postulate to do the proof. So, if you read all the directions a lot of times, especially with proofs, you're going to find that you can glean more information that'll help you to do the proof. Alright, so I'm going to start with the given statements. Jn is congruent to Ln. They've been marked that way. And Kn is congruent to Mn. And they've been marked that way. Okay, so according to this postulate, if we want to use only this postulate, the side angle side postulate, it seems like we've got one pair of sides right there and another pair of sides down here. So what we would need is the angle that's between those two sides, and if you write them on this triangle, you can see that that would be this corner right here, right? So on this triangle, we'd have to go side, angle in between the other side in order to get side angle side. And the same thing over here. If this is the side, and then this is the other side that we have pairs with going across, then this would be the angle in between. So the thing that we want to prove is really just one thing. We want to prove that this angle and this angle are congruent. So I'm going to prove that angle JNK is congruent to angle LNM. So since these two lines intersect at that point N, and those two angles exist on exact opposite corners in that intersection, then we can state that angle JNK is congruent to angle LNM because of the vertical angles congruence postulate. And so we have established a side angle side with the angle in the middle, congruent to side angle side corresponding on the other triangle, angle in the middle. So we can say that triangle JKN is congruent to triangle LMN by the side angle side congruence postulate. The next example, they have two parallel lines. AB is parallel to CD, and this line segment up here, the length from A to B, is congruent to the length from C to D. AB is parallel to CD, and line segment AB is congruent to line segment CD. Okay, so how do we prove these two triangles are congruent? Well, again, we're going to use the side angle side congruence postulate. And let's see. Okay, so if this side is parallel to that side and we have a transversal line right here, then I know that the alternate interior angles must be congruent. So angle ABC must be congruent to angle BCD. Or DCB. And then I know that if I have a side which matches up with a side down here, and an angle here, and an angle here, that I'm going to have to find a side here. So the top triangle, I have side angle side with the angle in between the two sides. And on the bottom, I would have a side angle side with the angle in between the two sides. So that central side is key. So to establishing the side angle side congruence. So CB would have to be congruent to itself to form that third pair of sides that are congruent. So that's all I got to do. I'm going to go ahead and write these down here, that angle ABC is congruent to angle DCB because of the alternate interior angles. Congruence theorem. And this side is congruent to itself. CB is congruent to CB by the reflexive property. It says that anything is going to be congruent with itself. And then finally, I have established a side angle side here on the bottom triangle, congruent to side angle side here on the top triangle. So triangle ABC is congruent to triangle DCB based on the side angle side congruence postulate. Oops. All right, next page. All right, these are the last two examples. Complete the proof. OM is perpendicular to LN, which means that it comes together at a 90-degree angle. And that would be true on both sides. And ML is congruent to MN, and that's been marked as such. So how do I prove that triangle OML is congruent to triangle OMN? Well, again, in this section, we're practicing the side angle side congruence postulate. And I have a side and an angle, and then I would need the side on the other side of the angle, which means I'd have to use this side to prove, or to demonstrate on my left triangle that I have a side angle side over here, this one would match with this side, this angle would match with this angle, and then that side would be the same as itself. So on this triangle, that would be my side angle side. So I have a pair of sides, a pair of angles, and then a pair of sides, which is one in itself, that correspond and are congruent. As long as I can state this third side is congruent to itself, and that would be easy given the reflexive property. So our statements are going to start with the given information. And, I would also have to state that these two angles are congruent, and we can do that as long as we know that they're both 90 degrees. So I could say that angle OML equals the measure, of angle OML equals the measure of angle OMN, which is both 90 degrees, because this line OM is perpendicular with LN. So because of the definition of perpendicular lines, I know that has to be true. So if their measures are the same, then the angles would have to be congruent. Angle OML would have to be congruent with angle OMN. So now I have my two angles congruent, so I have my angle pair. So this would be by the definition of congruent angles. When two angles have the same measure, then we can say they're congruent. Line 4 would be that, moving on to this, just that this last side is congruent to itself, thus forming our theoretical pair of sides, pair being in quotes, OM being congruent to itself. So that would be the reflexive property. And then finally, number 5, I now have my side angle side pairs, side angle side. Started with these as givens. I established this pair of angles that are congruent, and I established this side congruent with itself. So now, according to the side angle side congruence postulate, oops, and I'm writing it on the wrong side, I know that triangles OML and OMN are congruent by the side angle side congruence postulate. And then finally, the last example for this section. Again, we're going to be using the same theorem here, the side angle side congruence postulate. We want to prove that triangle ABD is congruent to triangle ABC. So let's see. If B is the midpoint from here to here, we could prove that AB is congruent to BE. And if B is the midpoint from C to D, we could prove that DB is congruent to BC, because it's exactly halfway between here and here, and exactly halfway between here and here. And then we would have a side and a side pair. We'd have this side pair for that S, and this side pair for that S. but we would need the angle in between. So if we have these two sides and those two sides, we'd have a side here and a side here on this triangle, and we'd need the angle in between those two sides, which would be this one right here, right? That would be our A part of our angle. So on this side, this triangle, we would have side angle side, and then this would correspond with that. Hopefully we can figure out a way for this angle to correspond with that angle, and then this side would correspond with this side, and they'd all be congruent pairs as you go across. And then we would have our side angle side. We'd have our two side pairs that are congruent and our angle pair in between them that's the same measure. So finally we want to prove that angle A is congruent to itself. Well, that one's easy. It's pretty straightforward. That's the reflexive property. You can prove that anything's congruent to itself. Oh, I'm sorry. That's not the reflexive property. It's easy because it's the vertical angle theorem. I'm sorry. Talking too fast, thinking too slow. The diagram clearly has two lines that are intersecting, like so, and then this angle would have to be congruent to that angle. I also wrote it wrong. That's not angle A. I'd have to give it specific names, wouldn't I? Oh my goodness. Here we go. So I would want to prove that angle ABD is congruent to angle EBC. And again, intersecting lines, the opposite corners have to be congruent because of the vertical angle theorem. So if we put all of that together as a formal proof, statements on the left and reasons for that on the right, we can start with our given information. And we can start with any one of these that we'd like to establish. Let's go ahead and say that AB is congruent to BE. AB is congruent to BE because B is the middle point. So by the definition of a midpoint, AB would have to be congruent to BE, since B is smack dab in the middle. Also because of the definition of a midpoint, since B is exactly in the center between D and C, then segment DB would have to be congruent to segment BC for the same reason. And then the angle in between, as I mentioned, that's two intersecting lines. The angles across from each other would have to be congruent by the vertical angle congruence postulate. Actually, I don't remember if they call it a postulate or a theorem, but that's really not important. So we've established our side angle side on one triangle and the corresponding side angle side on the other triangle, making sure that the angle is in between the two sides. So now we can go ahead and state that triangle ABD is indeed congruent to triangle EBC according to the side angle side congruence postulate. And this one actually is a postulate.